Okay, so thermodynamic processes and process functions. Okay, so as always, if you're confused with anything as we're going through, please just shout out and we can discuss. Okay, so a thermodynamic process, or we can say definition. A thermodynamic process is a change in the state of a system. Okay, and as always, whenever I say states of the system, I mean macro states of the system. So for example, if we have one macro state P1V1, we can move the system into another macro state P2V2, and then maybe into a third macro state P3V3. Okay, so this sequence of steps from one macro state to another is called a thermodynamic process. Okay, and we can illustrate this on a PV diagram. So we got P and V. Remember, this is our macro state space. We can go from state 1, maybe to some state 2, and then down to state 3. Okay, and then this process here, from going from 1 to 2 to 3, we call that a thermodynamic process. Okay, next definition is a quasi-static or quasi-equilibrium process. Okay, those are the processes that we're going to be interested in. So a quasi-static, okay, or quasi-equilibrium, equilibrium process is a process through a sequence of equilibrium states, and we know what that means. Okay, where we nudge, okay, so that's not very technical, but we'll get to that, where we nudge the system from one state to another. Okay, just a little note on this. In your PDF notes from the previous lecturer, he mentions a series of equilibrium states. To be more correct, we should say a sequence of states. Okay, so it's a sequence of equilibrium states. And by nudge, we mean a very small change from one state to another. Okay, so we're not going to precisely define what we mean by nudge, but just as a little note here, a large nudge will not leave the system in equilibrium. Okay, so this is kind of like a definition by example. So if we consider like a container with a piston, okay, it's filled with gas. If we have a very rapid compression of the gas, so a very rapid compression will result in pressure waves. Okay, and pressure waves, that means that the gradient of the pressure field is non-zero and the pressure changes with time. Okay, so We don't have uniform pressure spatially or in time, and so the system is not in equilibrium. So we've got like waves passing through. So the system is not in equilibrium. Okay, so that's the classic example of a non-quasi-static process. If you were to move the piston slowly so that the pressure can equilibrate, with each little step, then that would be a quasi-static process. So usually very slow processes can be thought of as quasi-static. Okay, because you give enough time between each step for things to settle out. Much like the pressure over here. Okay, any questions so far? Okay, cool. I've got a few more definitions to get through. So definition. A process, and by process, I mean thermodynamic process, is called reversible if you can return the system to its initial state via the same sequence of equilibrium states. And again, the previous lecturer has series written. That should be sequence. But so its initial state via the same sequence of equilibrium states. Okay, and we can look back at our first example of the 3-state sequence. You can have something like this. So PV, we can go from 1 to 2. Sorry, let's make a straight line there. So we go from 1 to 2 to 3 in this direction. So we start in state 1, we move to state 2, and then we move to state 3. This is reversible if we can go 1, 2, 3, and we can also go 3, 2, 1. Okay, if it's possible to go backwards along the same path. Okay, then we say that it's reversible. In other words, if we have the sequence 1, 2, 3, then we should get the sequence 3, 2, 1. Okay, so that is a reversible process. Just a note on that, on this idea of reversibility. On a microscopic level, all processes are reversible. Okay, so by microscopic, I mean we have full knowledge of all the particles and what they're doing. Okay, so all processes are reversible. However, energy and information may be lost. And so the process is not reversible. Okay, so due to friction or some other process, the system loses energy to the environment and so cannot follow the same path backwards. Okay, because it does not have enough energy to do so. Okay, but on a microscopic level, with all of the atoms moving around, if you have full knowledge of what's going on, you can easily just reverse that process. Okay, however, we don't have knowledge of everything. which is why we use the concept of macro states in the first place. Okay, so we don't look at the individual microstates, we look at the macro state as a whole. Okay, so that's just something to keep in mind with this idea of reversibility. Okay, any questions on that? Okay, so not too bad. Okay, and as we did last time, we're physicists, we like to classify things. So we would like to classify certain types of thermodynamic processes. So classification of thermodynamic processes. Okay, so we can group these different processes into individual categories based on some properties that it may have. The first one is called isothermal. Okay, so that is the first category. And in this category, temperature remains constant. Okay. The second category is adiabatic. And here, no heat is transferred. So remember what heat is. Heat is like work being done. It's the flow of energy from one system to another. Okay, number 3, isobaric. Okay, and then you see here it's got bar in it. That gives you the idea of pressure, right? You know, like your tires are filled to so many bars of pressure. Iso means the same, so isobaric, pressure remains the same, or pressure is constant. Sorry, just give me a second. No, there we go. So pressure is constant. Okay, and number 4, isochoric. Okay, I don't know what choric means. Might be Greek or something. But this means that the volume is constant. So choric has something to do with volume. Okay, I've got a question here. In the notes it says irreversible. Let's say irreversible process must be quasi-static. Okay, so the idea of reversible and irreversible is different to quasi-static. So if we look back at our definition for quasi-static, quasi-static just means that the process is a sequence of equilibrium states. And remember, the macro states need to be equilibrium states. So if we just look here, this just means, so quasi-static just means in our PV space, we go from one to another like that. So all the points in our PV space are equilibrium states. Okay, all the points in the space. So any path that we draw will then be a quasi-static process. Now, the idea of reversibility is different. Reversibility says that if we can go along this path one way, then we can go along the path the other way. Okay, so 2 different things. So quasi-static just means some path in this PV space where all the points are in equilibrium. Reversibility means reversibility or irreversibility is either you can go along the same path in both directions or you can't. Okay, so two different things there. Okay, so the idea of quasi-static just means that each point is in equilibrium. So if I just draw here, so we've got one point here, that's in equilibrium because it's a macro state. This point is in equilibrium because it's a macro state, and so on. Okay, all of those points are in equilibrium. I can connect them like this, and I get myself a thermodynamic process. So I've got my initial state and final state. This process here is quasi-static because it goes through equilibrium states. That's all you need to know about quasi-static, nothing else. The next thing is about reversibility. Okay, so they're separate things. Reversibility is if you can go one way, you can go the same path, but backwards. However, if energy is lost due to friction, then you can't go along the same path backwards, right? Because you've lost energy. You need to take a different path. Okay, so this is reversible. Reversible. And then a little note, if energy is lost, then the process is irreversible. Okay, so you don't need to mention anything about quasi-static or anything like that. Reversibility and irreversibility is a separate issue. Okay, so don't look too much into what the notes say there. They are separate things. Okay. Okay, so let's get back to our classification. So we have isothermal, temperature remains the same or constant. Adiabatic, no heat is transferred. Isobaric, pressure is constant. Isochoric, volume is constant. Okay, so those are just labels we give to certain processes that have these properties. Okay, and we can look at an example. Let's say we have an ideal gas. Example of processes. And again, by processes, I mean thermodynamic processes on an ideal gas. Okay, so let's say we've got our macro state space, so PV diagram. Like this, we start, let's say here at number 1. We move across to number 2. We follow this kind of curve here to number 3. And then we go back down to number 1. Sorry, that arrow is the wrong way. Okay, so it doesn't have to make a cycle, but this is just an example. For the first bit, from 1 to 2, we see that pressure remains the same. Okay, because we're on a constant pressure line. So from 1 to 2, pressure remains the same, so we call it isobaric. So from 1 to 2, it's isobaric. Okay, from 2 to 3, I need to give you a bit more information about this line, about this curve. So if we look at the equation of states for an ideal gas, PV equals nRT, we can take V over to the other side. P equals nRT times 1 over V. So we get a hyperbola kind of shape. Okay, because it's like 1 over x, it's a hyperbola. So if you get a hyperbola shape, we know that it must have constant temperature. Okay, for this to be a hyperbola, T needs to be constant. So from 2 to 3, that is isothermal. 2 to 3, isothermal. It's got a hyperbola shape. Okay, and instead of saying hyperbola shape, we give it a nicer name of an isotherm. Okay, so those lines of constant temperature, in other words, the hyperbola lines, we call those isotherms. Okay, so the lines with the hyperbola shape. And lastly, 3 down to 1. Okay, we see that volume is constant, so that's going to be isochoric. Okay, so that is from 3 down to 1. Okay, so that's a little summary of labeling the different thermodynamic processes. Okay, and just again with this example, we see that we went from state 1 to 2 to 3 back to 1. If we have that, then we call it a cyclic process. So a thermodynamic process, thermodynamic process that ends at the starting position or at the starting state is called cyclic. Okay, because it makes a cycle, loops around back on itself. Okay, any questions so far on this? Okay, so it's not too bad. Let's have a look at the next section.
Yeah, Brendan.
Yeah.
Back to the graph that you were using. I just wanted to confirm something about the reversible and irreversible parts. If the part is, the graph below. Sorry.
Yes, yeah.
Let's just use this one, for example.
Yeah.
If the part, for a reversible path, should it follow like the same path it used? For example, if I use path 1, 2, and 3 for reversible path, it should be 3, 2, and 1, not 3 to 1.
Yeah, so if you've got the path 1, 2, 3, then the reversible one would be 3, 2, 1. You just look at it going backwards.
Oh, so it's not reversible if it were to go from 3 to 1.
Yeah, no, that's a separate path. So that's not a reversible path.
Okay.
Okay, let's have a look at the next section on state function versus process function. Okay, so we looked at state functions already. So remember, those were the maps. So let's just write here, state function. Okay, so those were functions of a particular macro state. We could write it as f of PV, for example. That's a state function. On the other hand, a process function, maps a curve in state space to a real number. Okay, so if we look at this here, again, we'll look at our PV diagram, PV. Let's say we've got this curve here. So we've got initial state, final state, we go along this curve. A process function takes this curve, so it takes this curve and produces some real number given that curve. Okay, so it doesn't look at a particular state, like a state function is a function at a point. A process function takes the entire curve and produces a real number. Okay, so that is a process function. Okay, so now we need to do a little maths detour before we can get back onto process functions. And that is exact and inexact differentials. Okay, so you should have covered this in Math 251. and 212, but we'll go over it again just to be complete. Okay, so little maths detour. Exact and inexact differentials. Okay. So an exact differential also called a total differential, of a function, let's say f of x comma y, is given by df is equal to partial f partial x dx plus partial f partial y dy. Remember that from Math 212. Okay. Now we know from Math 212 and Clairaut's theorem okay, given such a function f, if it's nicely behaved and all that, we have the following theorem, that d by dy of df by dx is equal to d by dx of df by dy, the equality of mixed derivatives. Okay, remember that. So what we can do now is, instead of saying df by dx and df by dy, those are just functions of x and y, right? So what we can do is we can say df is equal to p of x comma y dx plus q of x comma y dy. Okay, so df by dx, that's going to be p, df by dy, that's going to be q. Okay, because they're just functions, I'm just going to call it p and q. Now, if we use the theorem on this differential here, so I'm just going to use the theorem. Okay, this gives us that dp by dy is equal to dq by dx. Okay, so this is the condition that we're going to be using to decide if a differential is exact or inexact. So if this condition holds, then the differential, sometimes called differential form, is exact. Okay, if it does not hold, it is inexact. Okay. Isn't that we use this for vector field to be conservative? Yeah, so it's the same maths involved. However, here we're not talking about vector fields, we're talking about differentials. Okay, but yeah, you're right, it's the same idea. Okay. So let's carry on. So now what can we do with these exact and inexact differentials? So note. Okay, and you're going to be proving this as homework. The integral, or I should say the line integral, of an exact differential is path independent. Okay, so what do I mean by that? Let's say I'm in the XY plane. Okay, and I've got a point P1 and a point P2. They're connected by some curve gamma, like that. Then, given some differential that I'm asking you to integrate along gamma, let's say that's gamma 1, then the integral along gamma 1 of P of xy dx plus Q of xy dy, okay, that integral along gamma is the same as this integral along gamma 2. Yeah, so it doesn't matter which path you take, you're going to get the same value. Okay, so it only depends on the endpoints. Now, this P and the Q, if we look back here, if it's exact, that means we can find this function f that gives us this differential. Okay, provided it's exact. Okay, we can find this function f. So here we're just integrating df. So that's going to give us f evaluated at the endpoints. So we're going to get f evaluated at P2 minus f evaluated at P1. Okay, so if you're integrating an exact differential, you only need to find this function f and then evaluate it at the endpoints. Okay, and then another bit here. Okay, you can try this out for homework. The closed loop integral of an exact differential, so P dx plus Q dy, is equal to 0 for exact differentials. Okay, so I'm going to leave that as your homework to try and do. Okay, so what you would need to do is, if we know this is exact, then it must be of the form df. Okay, there must exist some function f that can give you this. So the goal is to find f such that df, okay, so you find your f, you calculate df. This gives us P dx plus Q dy. Okay, that's again what it means to be exact. Okay, but this tells us how to find f. Okay, so we can find f using, well, we know that the part in front of dx must be df by dx. So df by dx must be equal to p, and df by dy must be equal to q. So we can use these two equations to solve for f. Once we have f, we evaluate it at endpoints and the integral is solved. Okay, so use that idea and show this. Okay, so that will be your little homework exercise. Okay, so all of that is with exact differentials. Now, exact differentials and inexact differentials, it's a bit hard to tell which one's which just by looking at the form of it. So what we do is we write exact differentials. So exact differentials. We use the following notation. df is equal to P dx plus Q dy. We use that notation for an exact differential. For an inexact differential, we use something different. It's d with a line going through. So df is, let's say, a dx plus b dy. Okay, it's like your h bar from quantum mechanics. but just with the D term there. Okay, so we use that notation for inexact. Okay, because it's hard to tell. If I just give you P and Q, you have to do the calculations to check if it's exact or not. This way you can see just at a glance what you're working with. Okay, any questions so far? Okay, let's give you some more homework just to work out this, this concept of exact and inexact. So number one, so this is homework. So number one, are the following exact or inexact? Okay, we've got a few here. So 2xy dx plus x squared dy. Number two, x dx plus y dy. And number three, cos y dx plus x sin y dy. Okay, so we've got these differentials. Are they exact or are they inexact? Okay, number two, find the function f that gives EF for the above exact differentials. Okay, so some of the above here are exact. The ones that are exact will have a function f such that if you find df, you get back to the differential. Find those functions. Okay, and number three, find the integral over gamma of p dx plus q dy for the following two curves. Okay, so let's just illustrate them here. We've got the following curve gamma 1 and then another curve gamma 2. Okay, so gamma 1 is given by y equals x from the point 0, 0 to the point 1, 1. And gamma 2 is y equals x squared for 0, 0 to 1, 1. Okay, so they have the same starting and ending points, but they're different curves. Okay, and I need to tell you what the P and the Q are. So for number one, it's for 2xy dx plus x squared dy. And for number two, it's going to be x squared dx plus x cubed y dy. Let's just throw in a third one here, x dx plus y dy. Okay, so that's all of the homework for today. Any questions on this homework? Okay, so has everyone copied it down? Okay, let's have a look at the last section for today. So work done is a process function. Okay, so pressure, volume, temperature, internal energy, all of those are state functions. So given a state, you can tell me what those are. However, work done, you want to calculate the work done by a system or the work done on a system, that is a process function. So to calculate it, you need some curve in the state space. Okay, and then the classic example of this, you got yourself a cylinder with a piston, like that, with some gas inside. If you compress this by an amount dx with some force F, so some force F here, you want to work out the work being done. Okay, so what can we do? We can work out the differential dW is going to be F dx, right? Force times displacement. Now, we know that this force is acting on a certain cross-sectional area. Okay, because it's this piston over here. It's going to look something like this. Okay, it's got some cross-sectional area to it. Let's call that A. Okay, so if you want to work out the force, you can take the pressure times the area. That's what force is. So pressure times area dx. Now, what is the area times dx? So if we look, again, just looking at the side here, if we move an amount dx and the area is A, you're going to get something like this. Okay, where this front surface here is A, this width here is dx. So dx times A, that's going to give us the volume of this little bit here. Okay, so this is going to be dV. Okay, so A dx is dV, so we get P dV. Okay, so that's going to be the work done if we compress this gas by an amount dV. Okay, or if the volume goes down a bit. Okay, so we can say, so there's different sign conventions. Okay, so I'm going to let you pick what sign convention you want. So you can either write things in terms of the work done by the gas. So work done by the gas on the environment. Or you can write things in terms of the work done on the gas by the environment. Okay, so it's just two ways of thinking about the same thing. The gas is pushing out on the environment, so the gas does work, or you pushing on the gas, so you do work. It's just a minor sign difference between the two. So we can say dW is plus or minus, depending on which way you want to think about things, P dV. Okay, and then that depends on the change in volume there. Now, this is the differential of work being done. If you want to find the total amount of work being done, we then have to integrate this. So the total work being done the total work being done, W. This pen. There we go. Okay, so W is plus or minus, again, depending on how you want to think about it, integral P dV. Okay, so that's how we get the total work being done. Now, this depends on the path taken, right? Because it's an integral of P dV. It might depend on the process taken. So if we look at our PV diagram, we could start in this state here. we end up somewhere over here. So the volume's changing, the pressure's changing. That depends on how you do the process. So you could go this way, or you could go this way, for example. So let me fix that. Okay, let's say you've got the path gamma 1 and you've got the path gamma 2. So the work being done is the integral over gamma 1 or gamma 2, depends on the path. So the integral over gamma. Now, in some cases, it might depend on the path. In other cases, it might not depend on the path. Okay, so in general, this may depend on the path. So in general, you would have to calculate. So given a certain situation, you can check if it's path dependent or not. Okay, but in general, this may depend on the path. And so we don't write dW because that would mean it's an exact differential. Instead, we write it with the line going through. So dW like that. Okay, and then in that case, the total work being done is the integral, again, plus minus, depending on how you want to think about things, over gamma, dW with the line going through. Okay, again, because it may depend on the path, we've got this inexact differential here. Okay, but if I give you a certain situation where we know that it is an exact differential, then you don't need to write that. Okay. Okay, so it depends on what you're working with. Okay, one more bit of homework, not too much. Homework 2. Find the work done for the following processes. Okay, so number 1, an isochoric process. Okay, from V1 to V2. Because remember, it's an integral over the volume. So I need to give you the change in the volume. Number 2, an isobaric process. Again, from V1 to V2. And lastly, an isothermal process. Isothermal process from V1 to V2. Okay, so find the work done in each of these situations. And just a question to ask yourself while you're going through this. Okay, why is there a unique path in all 3 cases? Okay, so just something to think about while you're going through those questions. Okay, because I didn't specify the path, but I told you what kind of process it is, so that tells us why it should be a unique path. Okay, so that is homework number 2. All right, any questions on this homework problem? Okay, so I will post the solution sometime next week. So that gives you some time to try it out for yourself over the weekend. If you do have any questions while you're going through it, please just post your questions on the WhatsApp group or through email. Okay, I'll be happy to help you out. So this homework isn't counting for marks or anything. So you can ask for as much help as you need. However, that hand-in problem, so number 1, remember that is due on Monday. Okay, and that is for marks. Okay, so homework problems, not for marks, but I do encourage you to do them. The hand-in problems, you know, if you're stuck and you need me to clarify something, I can help you out, but those are for marks and it's due on Monday. Okay, you can have a look on Learn 2022 for the exact deadline. I think I'll put it as midnight or something like that, but just have a look at that. Okay.
So the tutorials, the numbering is, I think I'm a bit confused over there for the tutorial, the numberings.
The numberings. Let me just have a look here. Let me just change my screen share. Okay. Let's see. Here we go. Part 1 tutorials. Can you see this?
Yes, sir.
Okay. So let's just check here. This bit here, this one, that's going to be for week 1. So that's week 1. So that's questions 1 and 2. For week 2, you're going to do questions 3 and 5. For week 3, you're going to do 4, 6, 7, 10, 11. Week 4, you're going to do these. Week 5, you're going to do these. Week 6 and week 7. Okay, so the bold numbers, they'll show you the weeks, and then the list of numbers next to it, those are the questions you have to do. So if we just look down here, where's this rotates? Here we go. So here are questions. Here we can see there's 1.1, 1.1, 1.2. Okay, so that was for the first one. And then here we've got 2.1, 2.2, and so on for the second part. Okay, does that answer your question? Does that clarify things? So yeah, for 1, we've got questions 1 and 2. So then that would be this bit here. So questions 1 and 2. Then the next one was 3 and 5. So let's see where that is. So here's question 3, the first law of thermodynamics. And then question 5, scroll down here. Here's question 5, entropy. Okay, does that make sense?
Yes, sir.
Okay, cool. Okay, but these tutorials aren't for marks or anything, but you know, you are encouraged to do them as practice. Okay, I will be uploading past test papers and test papers, exam papers, so you can go through what the test type questions are going to look like. Okay, but I'd focus on those hand-in problems and the homework problems. Okay, so that's more like what the test and exams and all that is going to look like. Okay, any other questions? Okay, cool. So I'll upload the video to YouTube so you can have a look. Same thing with next week, it's going to be online. And then in the 3rd week, we're going to have full contact. Okay, so no more videos in that case.
So
Okay,
but when we go to contact, we can still watch the other videos that he's posted as well.
Oh yeah, of course. So you've got all those videos as well, but I won't be making any more videos because you'll be seeing me in person.
Okay, sir. Thanks.
I've got another question here. Can you do 2.3 on the TUT? Yeah, sure. Next lecture, we can have a look at question 2.3. Okay, so I'll see all of you on Monday. Okay, bye everyone.